So we'll be talking about big data analytics for IoT data, which is Internet of Things. So the flow of the discussion would be that I'll be introducing first the Internet of Things and then various different components responsible for data collection, storage, and analysis. I'll be talking about some of the issues and types of data analysis we can perform on IoT data. Then I'll be giving you the idea about the characteristics of the big data. And finally, I'll be talking about 2 or 3, whatever time permits, the algorithm which could be executed on a distributed and parallel framework based on Hadoop MapReducer. Okay. So this would be the coverage of the today's discussion talk. Okay, so I start with that. The first thing is, what is Internet of Things? If you see the entire Internet of Things, then it is actually a combination of embedded technologies, where actually we experiencing the wired and wireless communication. The physical devices are there, like sensors, actuators, and others. Some other devices also can be connected, and all these devices are actually networked together and connected to the internet. So such environment is referred as Internet of Things. Okay, so basically if you look this particular picture, then you'll find that whether you are talking about a smart home or smart park or any sort of traffic, smart city, any industry, offices, buildings. So all these may be equipped with the physical devices for some sort of sensing you can say mechanism, which actually gather data, and then there would be some sort of processing may be done locally and then processed in layers, like it may be processed in fog or edge, and then finally it can be stored on cloud or any data centers as per your configurations. Okay, so this is what happening in the entire framework of Internet of Things. So what is the purpose of IoT? The purpose of IoT is to develop a smarter environment. That means environment was already in place. Only the thing is you just want to introduce some smartness in the environment in terms of data analysis, in terms of pattern generations, in terms of decision making, in terms of pattern based decisions. So, and also it is very much important that you save time, you save energy, and as well as the cost of the environment. So if you can actually make a trade-off between entire infrastructure and time, energy, and cost, so we look for optimal, or you can say configurations, then we actually talk about IoT. Okay. So as far as components, so we have physical devices, then we have processing networks, then we have data analysis, and then we have system monitoring. Okay. We'll talk about each of these. These are some, you can say, areas where actually have domains or applications where actually we are working in terms of data analysis. We have smart traffic, smart health. We have smart weather predictions, agriculture, then smart home. So you can see that what we have is we have type of data. In some data, there is you are generating massive amount of data. In some cases, you are streaming and all. And then there may be the case, as far as I told you, that processing framework, it could be edge or cloud or fog, it could be anything. Okay, so that is what happening in the system. What are the issues and challenges we are facing in IoT? So uh, just a minute. So we are actually handling high volume of data. We are also experiencing high velocity of data and different variety of data. Like it could be multimedia data, it could be like multimedia data like video, images, it could be a numeric data, it could be data of different types. Okay, so we're talking. This is very important that user should have some sort of abstraction, because otherwise it becomes a very complex thing. So we provide lot of abstraction for to the users, even in some abstraction at physical level, some abstraction at middleware, some abstraction at top layer like cloud or data centers and all. So whatever analysis is going on is here, and so we provide lot of abstraction to the user at this level as well. Because when we talk about parallel and distributed processing of the data, then actually we are providing high abstraction to the users at this level, because whatever framework we are using, this framework is itself providing a lot of abstractions. Okay? So that is there. Uh, Data privacy is something which is always be a part of any domain. So an IoT is something where actually we deal with smart homes, which is very private property. We talk about some smart offices, which is actually a domain specific to a particular service provider. So data privacy is very important, and obviously these days this is most important issues in any IoT applications, whether it is smart home, whether it is smart health and all, or whether it is smart building you talk about, or so many other applications could be. Okay. Data analysis, very you can say, though the analysis is already matured field in today's world, but still the selection of algorithms for a particular data of a particular domain is a very important and critical issue. The reason is very simple, that data might be a streaming data, data might be a big, large, or small data. So depending upon, you have lot many options in terms of algorithms. Even if you look on functions, then we have different functions like classifications, clustering, we have summarizations, associations and all. And within these categories, there are so many algorithms available to you. So the question is, which algorithms will be good enough for my particular environment? So I'm talking about a specific domain. Okay. So normally what we do is that we choose set of algorithms, and then we actually go for implementing all such algorithms and comparing on basis of accuracy, efficiency, some sort of metrics we use, and then we actually conclude that, oh, this algorithm is good for my domain. So that way also we are proceeding. Okay. Uh, this is something is we have uh, gathered from the internet itself, from one observation where actually we are talking about potential economic impact of IoT in 2025. Okay. So what we are, the first one which will be which we will experience in 2025 is that the high increase of users or consumers. You can see that at present we are having some sort of 4 plus trillions, which may go up to 11 trillion by next 4 years. Okay. Uh, what are the possible domains where actually we will be looking forward for IoT applications? Certainly be uh, individual human related to health, monitoring and all. Then home, retail environments, offices, factories, work sites, obviously traffic and vehicles, then smart cities or cities you can say, and then even outside like you'll be covering maybe sea and oceans as well in future. Okay. Uh, Obviously applications, each of them will be like as far as if I'm talking about outside and sea and also though I'll be looking for logistic routing in that case. If I'm going for traffic and all, then I'll be looking for autonomous cars, trucks and its navigations. Okay. Cities, certainly we are very much concerned of safety and health of the public, then resource and traffic control will be one of the important applications. So similarly, there are so many applications involved in each of these setups, you can say. The major, the boost will be in terms of industry and factories, where actually you can see that there will be a high boost in next 4 years. Then, as you know that even our country is working on smart cities projects. Even Allahabad is also one of the smart city project, uh, which actually going on, and we have done lot many work in Allahabad in terms of smart city implementations. Okay. So there is a large growth involved in these two areas, though there are growth in other areas also, like retail we have significant, we have outside also we have significant, but these two are going to be a, you can say, very much important applications. Okay. What we look for in these two, like in industries and factories, what we look for? We look for operations optimizations, we look for predictive maintenance, inventory optimizations, and obviously health and safety of the uh, persons involved in these domain. Okay. Whereas in city also we are very much concerned of public safety and health, traffic, resource, and issues like management of markets, management of opening and closing of different markets in different areas of the cities. Okay. So to have an optimal or optimized traffic and crowd management. So we are working in these areas, and obviously there is ample opportunity involved or present in these domains. Okay. Then we move to IoT data characteristics. So obviously characteristics of IoT data, if we look, then we'll have, you can actually have two categories, that is inherent and domain specific. When you talk about inherent sort of things, then certainly we'll be talking about big data, then distributions, then time series based data collections. Okay. Uh, Domain specific, then certainly semantics will be involved. Dynamicity could be when you where you are looking for mobility, the environment, dynamicity, and obviously reliability of the network, whether it is network is reliable or unreliable, could be a part of that. We can also deal with the statistical part where actually we look for periodicity of the data, correlation of the data, and obviously the Markovity property of the data as well. Okay, so we'll see one by one. As far as big data, certainly initially we look for velocity, that how fast the data is generated from the applications, a volume, that what the volume of data the particular application is generating for you. Like it could be generated by sensors, actuators, or it could be generated by some other devices which is involved in the environment. Okay. Heterogeneity is something which is actually a integral part of the IoT, because when we talk about the integration of different domains, that if I talk about smart cities, the moment I talk about smart cities, then traffic comes, the health comes, uh, uh, you can say office comes, schools, okay, industry. So when we talk about any city, then these are actually the almost integral part of all the cities. Then when we talk about sort of uh, data collections, so if I'm looking for a data center where actually I'm looking for all data should uh, come, then certainly in all cases, since these are actually different domains, so obviously there will be a heterogeneity, or not only heterogeneity, there will be a high heterogeneity in terms of devices, in terms of data, in terms of applications, in terms of environment as well. Okay, so high heterogeneity, not only across this interdomain heterogeneity will be there, even there will be a heterogeneity within intradomain also. So there could be, like if I'm talking about health, then there may be set of hospitals. It is not necessary that each of the hospitals could be using the same sort of systems or same sort of applications. So these individual hospitals might be having their own uh, environment or own network, where actually they are using their own set of softwares or network protocols. So there will be heterogeneity uh, within the hospitals as well. Okay. So heterogeneity in data is actually frequent and can be due to different data sources, data types, and networks, as I told you. Then we move to distribution part, that you know that metadata and sources tend to be spread spatially depending on the region of interest. Like you can see that you have some oil fields, you are looking for smart oil fields, or you are looking for smart cities. You can see that have sensor deployment spread over a large area. That means we are not constrained with small area or a building or office. Okay, like compared to the smart building systems, which is actually a collection of very dense sensors closely deployed, and obviously those data might be having high correlations compared to the data you are collecting from sparse sensors across a larger area of domain. Okay, so what is the ultimate thing which you look for is that collection of data at lower level, some analysis that could be done on middle level, and then you want to store those data into the top level, which is actually could be cloud or any data centers. Then between this cloud and data center, the physical devices, there is a possibility of implementation of what you call it as edge and fog computing. Uh, Sometimes we may confuse as well that edge and fog computing is actually synonyms of IoT, but it is not. Actually, if you look the layers, you'll find that this particular layer is actually IoT devices, whereas the top layer, which is either data centers or cloud, is actually where this is a centralized storage, where actually we wish to store all the data which is generating at this. Now, what we are doing is we are trying to do some analysis or say some pre-processing or some filtering or anything. So for that purpose, we actually introduces some of the nodes which is referred as edge node or a fog node. Always remember that obviously fog cannot replace this edge part, but edge can always replace fog. Okay, so it is not necessary depending upon applications and environment in which you are working. Okay, this is something what we look for is almost both are having the similar same sort of, you can say, motivations. That what you do is that we want to have computations local to data. Okay. So actually these two, edge and fog, is actually talking about this, that we want have some sort of analysis where actually the data is. Like you can see that you have IoT devices which collects data and you do some sort of pre-processing, filtering or analysis, and then finally you actually push the data into cloud or data centers. So in the middle of, you can say, between like pushing data from IoT to the cloud or data centers, you actually make use of this edge and fog. So that is, so this is nothing but it's a system server which actually acts as intermediate nodes and do some sort of computations just to have a trade-off between you can say it actually provides ease to the data centers or cloud to have a proper data to be stored. Time series, certainly in IoT, we are very much interested to store the data with a time variant and all. The reason is very simple, that there are certain set of applications where actually we are looking for prescriptive analytics, where actually what you do is that you generate pattern out of the data and then you take actions. Like for example, you found that your smart home, the fans and bulbs are switched on while nobody is in house. So you want to switch off your bulbs and fans. So that means you are very much like certainly this particular action is very much depending upon time. Okay, so you might be interested to have action of switching off the smart and fans at time t, but might not be interested at time t1. So that means the data which we require is very much with bounded with time, and actions are depending upon time. So action may vary with the same data with time. Okay, so that is the case. So the streaming data, certainly you know that data is transferred from the generation of storage processing location in the fly. Then we have other characteristics as semantics, dynamism, and a statistical uh, semantic. You know that it is actually providing some contextual information about the data. That actually what you do is that you are just adding more meaning to the data collected. Okay, so some set of rules or some sort of you can say informations you actually add on with the data, which can be inferred in a more valuable manner. Okay, dynamism. Uh, when we talk about, then we talk about some mobility, or we talk about some dynamic environment, or we talk about some sort of unreliable network. So obviously, when we talk about data collection and the period for which the data you are collecting, and obviously we are interested to have the to store the variations of the patterns of the data in terms of mobility, in terms of environment, in terms of network as well. So then actually we look for dynamicity in that case. Okay, if you look, we also look for statistical inference of the data also, because that helps a lot. Because if I'm interested to have a periodic data collections instead of continuous streaming of the data, so I may say, okay, every 7 days or every 7 hours or every 7 months I could be interested to have data to be collected. So when we fix the data collection in a period for a particular period, so that can be also part of the data collections. Obviously, when we talk about correlation, then certainly, as you know, that in most of the sensor network, uh, the neighboring sensors are having very high correlations in terms of data collections. And that is why we actually look for aggregations, inference, and many more things which is in place in today's world to optimize the data, you can say processing and data communication part, because that actually introduces a lot of optimization in terms of uh, yeah, communication cost. Okay, because instead of sending the high number of data, we can actually send the data in an aggregated form, so which can actually significantly reduce the cost of the communication. Okay, so correlation is one of the important part of the IoT data environment. Okay. Markovity, I think everybody is well known on this. Uh, in some physical quantities, which actually measured by the sensors, sometimes what we found is it is actually a function of their immediate previous value, or it is not dependent on sensor value or state beyond that. Okay, so there is always possibility of such property to be present in the environment. So you know that this particular set can be handled by Markovian nature of the data, and statistics are available for handling such data. Then looking on entire uh, infrastructure, devices, physical layers, middle layers, and top layers of the IoT and all, then the question comes, what actually mean is data analytics? As you know that motivation is already in place. We know that why do we require this data analytics? Because we have seen that there are a lot many applications involved in IoT, which actually talks about day-to-day activities, like, for example, smart cities, for example, health, smart health and all, monitoring and all. So we always look for, or it is very important to analyze the data collected and then proposing some sort of set of actions to be taken, which can actually improve the environment and as well as the consumers. Okay, so that is the motivation behind that. So it says the data analysis as procedures of the analyzing data, techniques for interpreting the results, data gathering that makes analysis easier or more precise or more accurate, and finally all the related machinery and statistical methods used. So that means you may use any set of algorithms, you may use any sort of statistical methods. The result which we are looking is that it should be accurate, it should be precise as well, and it should be easy to understand. Okay. Not only we are analyzing the data, but sometimes we analyze the knowledge as well. Okay. Because as I told you that by analyzing the data, you could generate a lot of knowledge, but out of those knowledges, there are some knowledges which has high utility and there are some knowledges which are having low utility. So I'm just looking forward for high utility knowledge. Okay, so that is what we do it. So overall, it actually carries the same thing which we are doing it in the simple data analytics parts. Only the thing is the domain of the data is IoT. So we are actually gathering data from IoT, but the ultimate analysis is same. Only the thing is what actually differs in this case is if you talk about any static analysis of the IoT data, it is same as any analysis, data analysis. Reason is what you're doing is you are actually applying your data analysis on cloud or data centers. So we already have data collections from IoT environment and we stored in data centers and clouds. So this entire IoT process is already done, and this is nothing but it's a data. So if you are analyzing this cloud data or data center oriented data, it is as simple as data analysis of any data. So all such methods, algorithms, or you can say any sort of like whether it is we are using information science or whether you're using mathematical statistical methods, whether you're using machine learning or deep learning and all, that can be applied on this particular part also. Only the difference will come when we talk about something which is distributed and we are looking for parallel execution of some analysis, maybe at IoT level itself, then it differs. And certainly you have to have some sort of alteration to be proposed for handling such cases. Okay. I think already I have introduced this part in the introduction talk. Just adding something is we have something like descriptive analytics, then we have diagnostic analytics, then we have discovery analytics, predictive and prescriptive. So I think all what we look for is I'm just saying you. The first one is descriptive analytics, always trying to answer the question what happened. Okay. Diagnostic, when I say, then we look for the answer of why something has happened. Okay. If you talk about discovery, then it is trying to answer that what happened that we do not know about. Okay. Predictive, the moment I switch to predictive, then I'm looking for what is likely to happen. That means I'm talking about some futuristic actions. I'm talking about something which could happen in future. It could be next day, it could be next month, it could be next year. So I'm just talking about some predictions. And the moment I'm talking about prescriptive analytics, then certainly I'm looking for that what should I do about what has happened or what is likely to happen. That means you have already data, you have analyzed data, you have some patterns, say 1, 2, 3, 4 and all. So what actions you are taking? for 1, 2, and 3, and also why you want these actions to be taken. So when you actually look for, you all actually what you do is that you do some sort of descriptive diagnostic analysis and predictive analytics. If you combine all these three, then it becomes your prescriptive analytics. That means I'm just looking for that what happened, why something happened, and then what is likely to happen. Then obviously what should be the actions I could take. This can be the part of predictive analytics with the consideration of prediction, descriptive or diagnostic analysis. Okay. So it is actually a combination of everything. So IoT actually involves all such type of analytics. Okay. Uh, these are some sort of existing analytic systems which was actually summarized by Marjani in 2017 in some paper. You can see that there are some existing architectures and tools available. So real time, we have some Grimplum and HANA, whereas some offline like Scribe, Kafka, Time Tunnel, Chukwa and all. Whereas memory level, we have MongoDB. MongoDB is very popular. Even we are using it in so many applications these days. Then we have business intelligence level, which actually talk about some data analysis plans. As far as massive levels, obviously, when you talk about large number of data to be or big data to be analyzed in a way of implementation by implementing some distributed framework and parallel processed. So that MapReduce is always part, and now Spark is actually having a significant role in this also. Okay. These are some applications domains where actually techniques is being used and was used. So this is for health, this is for transport. These are the IoT devices which is responsible for gathering the data. SN is actually talk about sensors, whereas MR corresponds to medical records. These are videos, sensors, medical records are used. You can see that what techniques we have used in some data mining and rules generations done, visualizations, some classifiers. So lot many things have done in this particular health. As far as applications, you can see that ECG health monitoring, or you can say neonatal care and this smart clothing monitoring and all. What has been used is this in some cases. So similarly in transport also video and sensors were used with different applications. Then you can see that some sort of day-to-day environment like your home and building monitoring, you can see that people have used sensors, videos, IoT data. I just let me know SM corresponds to is social media. Okay, so we have used social media for having cultural behaviors. You can see public safety monitoring done by video surveillance. Some wearable lifestyle monitoring is done by some sensors. So what methods you have used is some data mining, anomaly detections, video analytics. In case of environment, then we have, you can see that forecasting of wind forecasting or weather forecasting or energy system forecasting. In all cases, we have used social media and as well as sensors. And you can see that we are using all ML, deep learning, ANN, data mining and all. So all are part of the things. So that means entire data analysis domain is actually very much useful and used by this IoT environment as well. So this is industry-based applications where actually still we are using sensors, then we are using videos, then we are using some traffic data also. Okay. Even you can see that in some cases we are using ontologies, which is a very different area of work. Okay. So we are using ANN and sort of Gaussian and all everything. So you can see that almost all entire domain of data analysis is used in IoT. Okay. So if I summarize the entire thing, then you can always see in this way, where actually you can see that there may be a three important part of data analytics in IoT, where actually I'm looking for analytical value. I'm also concerned about performance, and I'm very much concerned about distributions and interoperability. Okay. Uh, as far as commonality is concerned, certainly you can see that performance always depending is actually talking about streaming or some edge or fog computing, nodes, in-memory processing, cluster, big data computing and all. Okay. This distribution and analytical value always is very much, the semantic technology is very much used for trade-off between these two, whereas distribution interoperability and performance could be handled by edge and fog, whereas analytical and performance could be handled by with some sort of in-memory processing and distributed and parallel processing of the big data. So cluster like a big data, when I say that means I could have my own clusters of information of systems, where actually we can create lot many systems to be clubbed together and can create a cluster for you, which can actually process your data in distributed and parallel form. Whereas some sort of framework like Hadoop and where actually we are making use of SDFS and all, that actually the framework itself is capable of having multiple systems to be part of that, and that can be used for parallel and distributed. Okay. So that is what we did. So so this is what we talked about till this particular slide, is that what is IoT, and what are the parts, layers, components of IoT, then what actually we mean when we talk about data analytics in IoT and all. So now the next we'll be discussing about that, as I told you, that either you are handling static data or you are handling some sort of streaming data and all. So either you can go for data to be stored in one place, or it can be stored in multiple places. So how to handle such thing in our case? So we'll be talking about big data and its characteristics, and then we'll move to few algorithms, how it can be used for such environment. Okay. So I'll be talking about those things. So I'm just taking 5 minutes break to have some water and all, then I'll come back. Yes, I think there is one question that can we use ANN for data analysis? So answer is yes. And actually these days ANN is widely used for data analysis, because any sort of perceptron learning you use is actually ANN, and that actually train data and you get some sort of pattern out of it. So yes, we can. So I'm just taking 5 minutes break. Okay, thank you. Okay, so shall I start again? So next is I'll be talking about some of the characteristics of big data, and actually I'll be talking about some examples through which you can understand that what actually these characteristics means. Okay, you know that as far as big data is concerned, then we were talking about gigabyte, terabyte, or sort of petabytes, which is actually 10 to the power 9, 12, 15 and all. Uh, these days we are very much, there are so many applications which talks about some gigabytes and all, and we are few applications where actually we are talking about brontobytes, and even in very near future we'll be talking about more than that as well. Okay, so that means we are actually having huge amount of data which is produced in the environment. Okay, so what actually means, like, the question is that why do we say that it is big data now? Because there is a very thin line of difference that where I say that, because data and small data and large data was already in place. Now this big data. So the question is how this big data is different from what we had large data now. So there is thin line of difference. And obviously these characteristics can define that difference. Okay. So that we are looking for. So we are actually looking for velocity, volume, variety, value, then veracity, variability, visualizations. I think these three are well known to us. I'm just giving you a few examples for that. For example, if you're talking about velocity, then you know that uh, Google performs almost 4 million queries per minute. So you can visualize the amount of data this Google is actually having it. And 20 plus million photos per minute. Uh, this, which is like the moment YouTube was actually conceptualized, very few hours of data were available on YouTube. But now, since we have travelers, we have, you can say, uh, related to videos related to food, related to travel, related to so many. So there are so many YouTubers are involved, whether it is music and others. So many domains are there. So you can see that what is happening right now, because this is a big source of income also. So people are actually using uploading 300 hours of video every minute on YouTube. So the amount of data you are generating. Every minute, something around 300 billion emails are sent and received. Sorry, not every minute. Over 300 billion emails are sent and received daily, if you look on. And then around 3.5 million tweets are sent in a minute. See this volume and velocity growth. Okay. So already I told you that we are talking about some gigabytes and more. So the moment velocity increases, the volume automatically will increase. Okay. Airbus generates 10 terabytes every 30 minutes and 640 terabytes in one flight. That means one flight means going and coming, that actually treated as one flight and all, and that can generate 640 terabytes. So you can see that if you have multiple flight in a day, then it can generate huge amount of data for you. Self-driving cars will generate 2 petabytes data every year. Actually, we are in era of self-driving cars, and these self-driving cars always generate so many data because that data itself will drive that car because we actually uh, take actions based on those data. Okay. So this was the predictions of last year. You can see that by the end of 2020, there was like we were actually experiencing the 50 times the amount of data that we had in 2011. So obviously we are at 2021. So this particular times could have been increased by maybe 55 times and all. Okay. So that is what the case is. Variety, you can store data into database sheets. You can have email, photo, audio, or PDFs. Could be anything, which could be, which actually talks about variety. Value is something which talk about that any data is no good unless we can turn it into value. That means suppose what we are talking about, you have data of say consumers. Now if you can discover consumer preferences and sentiments, then only this becomes your value. Okay. If you actually analyze the data and you actually you are actually offering some sort of offers based on locations, that actually value of the data. Okay. Like in case of flights, if data can lead to the prediction that some equipment might go for failing, then you can take action accordingly and you can save life as well as loss. So that is value. Then veracity, the question always comes that are the results meaningful for the given problem space? That means actually you are talking about interesting patterns. What analysis, data analysis produces is patterns. What we are looking for is interesting patterns. Okay. So we always look for data quality and understandability of the things. So especially you can say automated decision making where no humans is involved anymore. You need to be sure that both the data and the analysis must be correct. Otherwise, it may create problem in the system and system might lead to inconsistent state. Okay. Variability is something which is very much talking about such data where data actually you can say tells you different meaning at different time. That means you have a same data D1, but at T1 it has a different meaning. Same data D1 at T2 it has a different meaning. So this is actually variability beta. For example, let's say this example I took from the some source. It says that suppose a bakery sells 10 different breads. This is what variety you are seeing. That means you have emails, you have photo, you have videos and all. Okay. Now you imagine that you go to the bakery and 3 days in a row, every day you buy the same type of bread. So each day it tastes and smells different. That means I can say that I'm having some sort of camera. The camera is producing some images, but day one I'm getting some different interpretations. Day two I'm getting some different interpretations. Day three I'm getting different interpretations. That is what we call it variability. Okay. So that is, and that is very obvious. is part of any sort of such IoT device environment. Visualizations where actually uh, business intelligence people are involved, where actually what you want is that you want to put the data or data analysis, output of the data analysis in a form that it can be very simple to understand. So it can be, yeah, the view can be one dimensional or multi-dimensional and all. So if you can provide multi-dimensional view of the pattern and data, that could actually uh, be very easy to interpret the data analysis by the upper management. So all such visualization techniques talks about that. So all these characteristics present in the data or big data environment, then you refer that environment as big data environment. Okay. Sources, as you know, that it is whether it's the smartphones, IoT, emails, blogs, Google, YouTube, or any web systems could be possible source of such data. Okay. So this is what big data sources. Okay. Now the question is you know that uh, you have IoT environment, you have data, you have big data now. Now the question is how to process it. The answer is, the first thing is that first you have to have some sort of environment which can process the data in a distributed manner and can process the data in parallel. So the answer is, the first one is that Hadoop can do that. Okay. So why Hadoop? The motivation is that you want to process huge amount of data on a large cluster of companies, because we realize that it cannot be handled through one point. Okay. So we need large clusters. Certainly, individual clusters or manual clusters building quite be expensive in nature. So what we look for is that we look for efficiency, reliability, easy to use, and it should be open source as well. So we need some sort of common infrastructure which can handle such. It can handle also failure of nodes, environment. Okay. So this is what looks like if you talk about Hadoop. You have switches, which is known as rack switches. We have aggregation switches, and then there are individual nodes. And the beauty of this particular framework is that you can add nodes as and when required, and you can also detach nodes as and when required. So as far as nodes are concerned, you can see that each rack can take 30 to 40 nodes. Okay. It can have 3 to 4 gigabyte uplink, or rack internal can be of 1 gigabit. Okay. So it's a very massive environment which can handle massive data. Uh, in Hadoop, this HDFS is the important part, because this HDFS actually tackling all the informations of individual nodes and how to store it, how data can be stored and all. So all these done by HDFS, distributed file system. The goal is very simple. It can handle 10K of nodes. You can see that how many huge amount of nodes it can handle. 100 million of files it can handle. It can handle 10 petabytes, and it can handle more than that also. Okay. So we do some sort of aggregations also. We make use of optimal use of bandwidth in this case. It also automatically detects failures and recovers. So it actually is having a very nice environment to implement huge data processing. So this is typical, you can say, which is possible in the distributed file system, that files may be broken into blocks. You can have a data coherency, which is actually that you can write once and read many times. Obviously, client can only append the files, existing files. Okay, we have a namespace system, and then we have a slave nodes, which actually be monitored by namespace itself. So if you look on the architecture, then it will be like this is node which is responsible for everything. It stores metadata and all, and it acts as the boss or coordinator of the all individual nodes. So these nodes can be configured under racks handled by name node. So that is what typical architecture of SDFS. This is one example that suppose you have data like this. So what we are doing is that we are doing some sort of replications. And these replications can handle actually the failure, individual failure or a rack failure. The reason, and these replications could be intra-rack or inter-rack as well. So the nodes are there. Suppose this is node 1, node 2, node 3. Then this way I can distribute the data. So I'm putting this 4 here, this 3 here, this 3. You can find that these are replicated. These are replicated. So each data bunch block are actually replicated just to handle the failure. It may be node failure or a rack failure. So that can be. Okay. So this is very important for that. So the entire Hadoop cluster architectures will look like this. There will be a job tracker, there will be a DFS master, which is name node or namespace, we call it. And then these are individual nodes, or you can say that these are organized under rack configurations. Okay. So different racks with different set of slave nodes could be the part of that. So job tracker is actually that client submit a job, and then job tracker actually gives assigning the jobs to the nodes and keep track of those jobs, whether the slave nodes has completed or not completed or in what stage it is. And then all coordinations done by HDFS master. So this is what happening inside it. As far as users of the Hadoop, so these are users, and this is a not exhaustive list. There are thousands of users of Hadoop already in place. So the idea is that move workers to the data. That means store data on the local disk of nodes in the clusters and start up the workers on the node that are data local. Okay, this is first thing. Why do we require that? Because you don't have enough RAM to hold the data. Or obviously disk access is slow, but disk throughput is reasonable. This is the limitations you will be carrying about, and that this limitation actually leads to the Spark introductions. Later we'll see. Okay. So we have Google file system, which is actually used by Google MapReduce, and we have HDFS is used by Hadoop MapReduce. So simple divide and control methodology would be used by what we do is that here you submit your work, and the work are divided into multiple chunks, and these works can actually go to the worker. That means individual slave nodes, you will be submitting it, and these nodes actually generates results for whatever work you have assigned to the nodes, and then ultimately you combine the results and you get out. So it is basically following the technology which is referred as divide and conquer. Very famous example of divide and conquer methodology of which can be seen in Hadoop is that you have a very big data, you split the data. So you have 1, 2, 3, n nodes you can have. Then each node actually performing this count and part. So each node generating R1, R2 and Rn, and then it is merged and you get the entire word count of entire data at space. Though it looks very easy, but it might be easy for word count, but it might not be easy for other applications. So each applications will actually carry very specific execution methodology and flow. And obviously it requires some sort of alteration in terms of, you can say, the implementation of the particular algorithm on Hadoop MapReduce. Okay. What are the challenges actually involved in parallelizations? Because as you have seen that that Hadoop framework can actually distribute data over the nodes, and each nodes can process the data locally. The challenges are actually, how do we assign work units to the workers? What if have more works units than workers? Obviously, the coordinator has the responsibility to divide the work and you can handle, but suppose you require more workers to be there, then what will happen? What if like your requirement is that workers need to share their partial results? What sort of aggregation, how this aggregation of partial results could take place? That how do we know that our workers have finished or not? And what if happens that what if suppose some worker dies? So obviously these are challenges always be there. Not only these, then we have difficulties as well that we don't know that order of the work, the execution of the workers. Then we don't know that when one worker is interrupting any other workers also. We don't know about the sharing of the data also. Okay. Certainly we have some mechanism like a locking, unlocking, then we have some conditional variables, barriers, which can actually handle some of the conflicts, okay, or can actually manage the consistency. But still we have race conditions, deadlocks and all. So what we say is that this the Hadoop framework provides you a lot of abstractions as a user, but it still says that be careful while implementing any sort of application on such framework, because there is always possibility of some sort of problems may occur at any stage of the executions. MapReduce is actually a programming framework for distributed computing. It uses simple divide and conquer. And obviously, you know that smaller units of work can be processed and it can be processed parallel. So what are the things can be possible when you do large data processing? Then obviously it can iterate, uh, it can extract something from each of the partitions. Obviously, shuffle and sorting of the intermediate results will be done. You have to have some sort of aggregation of intermediate results also, and then finally you go for final output. So you are doing lot many things for any large data problem when you are actually going for distributed and parallel executions. So that means you need to provide some sort of functional abstractions to the users, and we are providing in this also. So if you look the Hadoop MapReduce, then what is required to be provided by the user is that mapper function and reducer functions. So this is a key value pair. Okay. So obviously mapper can produce keys and values, whereas reducers with the same key, the values can be aggregated. Okay. So that can be. Rest everything will be handled by the frame. That means you are just to do this. Rest everything. Everything means everything. Whether it is talking about scheduling, data distribution, synchronizations, error and faults, this all will be handled by the framework itself. Okay. So what you need to do is that what is map, what is reduce, what is combine, and what is partition. So generally we express everything into MRCP, map, reduce, combine, and partitions, and rest all abstractions will be provided. So it's a very easy environment where actually you can process huge amount of data, or you can apply any set of algorithms which could actually produce patterns for you. Okay. So simple, what we do is that we already have big data, we already have slave nodes. Each slave nodes will go for mapper functions to be there. Each slave nodes can have reducer as well. That not necessarily the always reducer will be the same as number of mappers. Less number of reducer can also be a part of that. Okay, depending upon it. Simple key value pairs will be there. So what actually mapper does is that you generate key value pairs like this. Each of the, like this is node 1, node 2, node n I can have. And obviously these are intermediate key value pairs will be arranged like this. What reducer does is that, as I told you, that with same key, these are the values across the mappers. With the same key, these are the values. So these values can be aggregated. So it is actually these values aggregated and will produce this. These value aggregated will produce this, and similarly this. So this part is the work of reducer, whereas this part is work of map. Okay. So same example, I can see the word count executions. So these are the documents. So each of these are node 1, node 2, and node 3. So mapper functions executes, and these key value pairs will be generated. Then these two reducers actually aggregate this and will get this. If you minutely observe, then you will find that what is happening is the is appearing twice. So the is coming as 1, the is 1. So we are not writing here the 2, rather than we are writing the 1, the 1. So this is where something which comes is combiner. Okay. So this combine is actually an optional component. So this combine can be actually implemented over this MapReduce framework when this need to be done. That means you want to aggregate here itself this third to be 2, then this combiner will do that, and then actually that actually make ease to the reducers. So that is what happens. So what is happening is, so this is my M, this is my C, this is my R, and this is my P. Partition, mapping, combining, reducing. So this is what MRCP is there. So the entire this particular work is nothing but the function of MRCP. Okay. So this is what happened. Why do we require this Spark? Because Spark can actually replace this MapReduce. Sometimes it really does not replace MapReduce, that it also actually executes on top of the MapReduce as well. Why I am saying top of the MapReduce is suddenly you know that we have a Hadoop and MR and all, and then we have a Spark. What I am saying is the huge amount of data, so big data you have and all. So obviously, as far as big data processing is concerned, MR can do. So MR is having some limitation that it is actually disk working on this throughput, whereas this is working on memory. So obviously comparing to these two, this always be fast. So the reason of moving from MR to Spark is that previously disk was quite cheap in nature and memory was quite costlier. But we are now moving to the era where actually memory becomes cheaper as well. So certainly we can have more memory to be part of your architectures. So I can process faster than what we are not able to do maybe 10 years back. So this fastness actually introduces this Spark, which is actually executing on memory based. But still Spark has the constraint that it cannot handle still the huge amount of data, rather than it can handle big data, but up to some extent it can handle. After that, still the MR is capable of handling that data. So you can say that Spark could be referred as leopard, or MR could be referred as, you can say, bear. That means एक भालू है, दूसरा चीता है, एक fast है, and this. Okay. So it was primarily written in Scala, whereas now it is supported by Java, Scala, Python, and R as well. Okay. This is what these are the components of the Spark, where actually you do some Spark SQL, then Spark streaming, then machine learning library, then we have GraphX. If you look on this, then Spark SQL is actually a distributed framework, which is actually doing some structured data processing and semi-structured data processing. So SQL stands for structured query language. Data streaming is scalable, high throughput, and fault tolerant streaming processing does. Machine learning library, it actually gives you the facility to execute machine learning algorithms with high speed. Whereas GraphX, some APIs are available which can handle the graphs, and that can be executed parallelly also. So you can actually work on network graph, and you can also store those graphs as well. Okay. If you compare Spark and MapReduce, so as I told you that Spark has been found to run 100 times faster in memory and 10 times faster on disk. Spark is used to sort 100 terabytes of data in 3 times faster than Hadoop, MapReduce in the 1/10th of machine. Okay, so this is what the big difference between these two. So obviously Spark always be better for machine learning application, because you know that machine learning applications are very computationally intensive applications. So Spark can actually provide some efficiency in terms of speed. Okay, so you can also go for naive Bayes or k-means algorithms to be executed. Okay, so let me give you one or two examples that how it is big data processing could be done, and what sort of alterations or execution sequences need to be changed to have a distributed and parallel executions. So I'm just taking the same algorithm which we have discussed in the very first talk, that is market basket analysis. You know that how a priori executes. So we have this a priori algorithms where actually we have seen in the last talk is that how this can be generated. That is, we are generating L1, then L2, then L3, and then we move to go for association rules generations. So, and this is the formula where actually you go for ARs. So this already we have covered. So what I'm trying to do is, what I'm trying to tell you is that how it can be parallelized. So this is way. This is my node 1, this is my node 2, this is my node 3. Okay. This is my node 1 data, node 2 data, node 3 data. So this is my D1, D2 and D3, and D is nothing but D1 union D2 union D3. So this is the case. Okay. So what we do is that you can actually apply a priori and you can generate candidate sets for this. Okay. So you can see that obviously this is candidate set 1. So I'll be going for 2, 3 and say K, and similarly L2, L3 and LK. So normally in one go a priori executes all these. But what is happening when you are trying to have a parallel executions, what you want is, since you have to merge the intermediate results, and obviously finally also you have to generate the final results. So what it does is that the intermediate results must be shared in each iteration of a priori. Okay. The reason is simple, that what we have done is C1, C1, C1 we have generated. Once you generate L1, so this is 2 plus 2 plus 3 is 7. So this is 7, sorry, this is 7. Some sort of mistakes were there. And then 2, 3, 4, 5 is there. So what you generate, L1 you are generating, which is a aggregation of all three segments. So what we are doing is, we are aggregating the C1 of P1, then C1 of P2 and C1 of P3. So it is actually what you are doing, that you are union taking aggregation of this. And then next C2 will be generated based on the common L1, which is passed to each of the nodes. So this is the arrangement which could be done for a priori algorithms to be executed, distributed and parallel. Okay. So similarly, the same thing, the L2 will be aggregated for the next iteration, and similarly it will go, and finally it can actually generate L1, L2, L3 and LK, and then reducer has the responsibility to aggregate all these and can generate the final L. So this is what happened. So you can see that what is happening is simple, that each mappers can generate, and reducers has the responsibility to basically join or aggregate the results generated by each of the mappers. So, and details I have already seen that in each iterations, the intermediate results will be joined and will be passed to the each of the mappers for the next iterations to be executed. So the intermediate result, aggregated results of the intermediate results will be the input for the next iterations. So this is what happening. The next is k-means clustering, which is I think k-means is well known to you. If you are not aware of k-means, let me tell you one thing is very simple. K stands for number of classes and means is actually a centroids. Okay. So what we do is that we randomly take number of classes. So in this case, k equals to 2. So we took as class 1, class 2, and we are assigning randomly 1 and 4 for that. Okay. So 1 is this and 4 is this. There are two features involved, A and B. So this is my first centroid. Then what we do actually, that each of these data will be compared the distance between these two data with these two means, and closer will win. So what we do is we calculate the distance of, say this is my M1 and this is my M2. So distance between M1 with each of these individual data, distance of M2 with individual data, and which one is minimum will actually be, the data will be placed in that actually cluster. So with this particular fundamentals, what we have seen is that the individual, the cluster 1 and cluster 2, if you see, then you will find that you have cluster, in cluster 1 we have 1 2 3, and whereas in cluster 2 4 5 6 7. Once you have these particular distributions you get for k means, then we actually go for averaging the means. So you'll be getting cluster 1 in this, and now the mean is this. The previous mean was this, now the next mean is this too. With the same thing we'll be doing, that this mean 1 will be replaced by this mean 2 will be replaced by this, and then again the d1, all the data will be, distance will be calculated, and then finally the closer will win. And then accordingly what we found is in cluster 1 there will be 1 2, and in cluster 2 3 4 5 6 will be 6 7 will be there with this mean. If any two successive steps or iteration there is no change in the cluster, you can stop k-means there itself. So that is what k-means does. What actually we do when we try to implement k-means in a distributed and parallel manner, same way this can be done, because as you know that data can be distributed across the, so you are distributing in n nodes, and now you are actually, mappers are responsible for executing the k-means. Now the question is, could mappers execute k-means entirely in one go for all local data, or can we have some sort of sharing of intermediate results, so that it can provide ease in the system? Yes, the reason is very simple. Just take an example, then it will give you the idea. What is happening is that suppose you are distributed in node 1 and node 2. So you have d1 and d2 of data d. Now you are applying k-means here, k-means here with some, so mapper 1 and mapper 2 will be executed. Now if k equals to 2, then this will be generated this. The reason is what we do the arrangement is, if you are randomly pick mean for two classes, say I have collected mean 1 like this, say R and S, then these two will be R and S. And all the data which is happening will be mapped in these two. Now certainly when we go for improved mean, then I'll be getting some mean which is say M1 dash, this is M1 double dash, this will be M2 dash, this will be M2 double dash. Since these two are same, sorry, this is M2 dash, this is M1 dash, and this is M2 double dash. Okay. So what we require to do, that before going for next iteration to be executed, these two must be averaged out, and these two must be averaged. The reason is why, because whatever average I am getting M1 dash and M1 dash of two mappers of this, like you can say that this is of mapper 1 and this is of mapper 2. Okay, so you have to have this average, and then you have to average of these two. So that will give you the next iterations mean as M1 and M2, and this need to be passed to each of these mappers. The reason is very simple, that when you actually achieve the last iterations, or where you stop the k-means to be executed, there must be some criteria where actually I can merge the cluster of across the mappers. So since we are sharing the means in the intermediate iterations, so in each iterations, the mean becomes uniform for all the mappers. So in the last iterations, mean will be uniform also. So in that case, each of the mappers clusters can be merged and we can get the global centroid, global clusters. So that is what arrangements we could do. So that we do also. So simple implementations, what we have to send, the same thing is there. That key will be cluster ID, values will be coordinates, which A and B you are talking about, and simple, and then you can see that the reducer receives the input from the combiner and then it calculates the weighted average of its input, which computes the centroids of all key clusters. So this is the work of the reducers. And then iteration continues until the convergence arises. So this way, k-means could be executed in MapReduce framework. The last algorithm which I am going to describe is DV-scan. DV-scan is actually a very famous algorithm for clustering. This does clustering, and this is actually density based clustering. Okay, so DV-scan actually talks about two things which is very much important, is epsilon neighborhood and minimum points. So epsilon neighborhoods and minimum points are two criteria. Oh, sorry. So sorry. So what we have is that, say these are the points. This is the data, suppose. So it says epsilon neighborhood. So we are talking about epsilon distance and minimum points. These two are user defined. What is? I say 1 centimeter as epsilon. Minimum points, I say that minimum points will be 4. So what it does is randomly pick any point, go for 1 centimeter, take a circle. So you count the points which is coming within the circle, 1, 2, 3, 4, 5. So within this, I have 5 points. So it actually satisfies the 4 points criteria. So I can say this is my first label of clusters. Similarly, I can pick any boundary points and I can go for this 1 centimeter. And similarly, I am going for like this and those. So what is shown out here is the same way. So you can have like point this becomes your first level of clusters, then with this first level of cluster, with this, then second level of cluster, second, third, fourth, fifth, sixth, and so on, you reach to here. And all these are density connected points. So the clusters, if you look, then it will be like shape like this. So this is a very arbitrary shape of clusters it generates, and it generates on the basis of directly density reachable and density reachable points. So what does it mean is that given PQ into data points, if Q belongs to epsilon neighborhood means that with point with epsilon distance, this is all the points is epsilon neighborhood points. Okay, then Q is directly density reachable from P. So this is directly density reachable from B. So this is what we do. Density reachability says that if this is 1 epsilon distance, this is 1 epsilon distance, this is 1 epsilon distance. So since you are reaching 1 epsilon distance and you reach to this place, so all these are referred as density reachable. So it says that from P, if there is a sequence of points P1, P2, Pn, such that P is P1, Q is Pn. So I can say that this is my P1 and this is my Pn. Then each Pi plus 1 is directly density reachable. That means each is having this part. Okay. So all these points are referred as density connected. And this consists of one cluster of the data. So this what is happening in this case is, so what is happening is that you have data points like this. So you start with this and then you actually go for this to be one clusters. Then if you move to other, then you look for this will be then another cluster, then this will be another cluster. So it can generate such clusters. Randomly choose one point, go for all these density reachable points. Once it is over, then you go for another random point. Then this process will go on until all the points are mapped to some of the clusters. So it will generate arbitrary number of clusters and arbitrary shape of clusters. The question is how it can be parallelized. Okay, the answer is that this was the architecture proposed in one paper, which is MR based DB scan. So that talks about that how it can be partition, data can be partitions, then DB scan can be executed across the mapper. So what is happening in this case is that your data is distributed across say D1, D2 and Dn, and each M1, Mn mappers are executing DB scan. And DB scan always stands for density based spatial clustering with noise. Okay. The question is that suppose mapper 1 and mapper 2, they have generated say two clusters in mapper 1, say another clusters, three clusters in mapper 2. Now the question is that a reducer has the responsibility to merge these clusters, and certainly you will have the generality of global clusters generations. So it may be the case that it may be that these can generate some three clusters out of it, or maybe four clusters. So it depends on whether I can merge these two or these two or these two, three and all. So that can happen. So for that merging purpose, this particular thing is proposed. So what is happening is, this is my, so as I told you that cluster of one and cluster of this. So I'll consider the cluster of this and cluster of this as this and this. Then with epsilon distance, I'll be generating the inner region. This is inner region. And this with epsilon distance of this, I'll be going for outer region. So what I'm trying to do is that I have a cluster this, I have this is C1 and this is C2, this is C1, this is C2. Now I'm just trying to find out whether these two can be merged or not. So I have created first the outer region and inner region of both, which is nothing but epsilon distance. Whatever epsilon you have decided while doing the clustering. Now, with some at where the boundaries are C2 and CU lies, I can pick some random points P. I'll go for epsilon distance and I'll go for a circle out of it. Investigate this. If first few points in C2 and few points in C1, C1, then the answer is merge. Otherwise, do not merge. Why? As we know that this point is density connected with all the points of this cluster, and this point is density connected with all the points of these clusters. If this point and this point lies in this particular area, then obviously this point is density connected with this and this point is density connected with this. So hence all the points of C2 and C1 is density connected. So by the virtue of density reachability, I can merge these two clusters. So such investigations need to be executed for all the set of clusters to all the set of clusters for merging. So this is actually done by the reducer part. So hope this is known to you. Apart from this, there are some MR based random forest. Since I'm running out of time, so I'll not go for this. Simple, when we go for that, it looks like that this is maybe some sort of tree can be generated across this, and some voting criteria can be implemented to have some final class. And so you can go. There is one paper which actually talks about MR implementation of random forest also, and that is very easy to execute, so that is not a problem. So what are the research issues involved is still there are a lot many algorithms which need to be applied on big data, because as I know that scalability is something which is a problem, is a major issue. Okay, because as you have seen that k-means, or you can talk about a priori, both we are actually not efficient for a larger set of data. But big data, it is not efficient. So what we do is that we actually arrange the entire environment in a way that it can be executed for a big data also. Okay, or it can be implemented for big data also. Certainly, since we are doing parallel distributed, then accuracy always be a big concern for you. So as many metrics you can use to improve the accuracy or alterations, you can actually do that. That is always be a good research issues. Real-time analysis, as you know that these days we are working on data streaming, which is real-time, and we are also looking for analysis of such data on fly itself. So that again is very important area of research, which talks about the compatibility of the algorithms, the applicability of the algorithms, and the scalability of the algorithms as well. So that is what these areas you can always explore and can actually go for research. Okay, so you can reach me with this email ID, and I acknowledge all the authors and websites whose content was part of my lectures. Thank you very much. If you have questions, please let me know.